So today I want to discuss why intermolecular forces are important. So we've learned about intermolecular forces, what they are, and how we can try to assess their relative strength just based on the structure of a molecule. But we haven't actually gotten into why that matters. So intermolecular forces, we've said, are the force holding different molecules in a substance together. So in a glass of water, the intermolecular forces between those different water molecules are what help all of those water molecules stay together in your glass as one substance and not just fly apart all over the place. So intermolecular forces actually affect a lot of different things. So when a substance has really strong intermolecular forces, that means that the molecules are highly attracted to one another. They are really, really stuck together, and that makes them difficult to pull apart. So this affects quite a few physical properties of a substance. The two we're going to focus on for today are the melting and boiling points, since those are the things that are most familiar to us. It also affects something known as the vapor pressure, which we'll get into a little bit more later in the course, as well as the viscosity or the thickness of a liquid, and a bunch of other things that also has an impact on the chemical properties as well, how something reacts with other things. But for today, we're going to focus just on the melting and boiling points as sort of the clearest example of the effects of intermolecular forces. So if we take a look at these diagrams of a solid, a liquid, and a gas, we can kind of see what's happening to the intermolecular forces if we think about these different states of matter at this particulate level. So every place that two molecules touch represents an intermolecular force. So anywhere that two molecules are coming into contact with one another, they are attracted to one another. So in the solid, we can see that we have loads and loads and loads of places where our different molecules, whatever these orange little balls are supposed to represent, we have loads and loads of places where our molecules are in contact with one another because they're in this very compressed form. They're in this very compressed, rigid lattice type structure. So basically every molecule is in contact with another molecule on every side. So we have lots and lots of intermolecular forces, and as we move to a liquid, we can see that there are fewer. Our molecules are still largely in contact with one another, but they do also have sort of a little bit of open space around them, and in a liquid, we know that the molecules are moving around more too. So going from a solid to liquid, or melting, is disrupting some of our IMFs. Some of our intermolecular forces are being broken or disrupted. That in the liquid we don't have as many, we don't have as strong of intermolecular forces because our particles are moving around more, they're not fixed in one place. So there are fewer intermolecular forces between them. And then we can see in a gas that our molecules are pretty much completely separate. There are very few intermolecular forces in a gas. So in going from a liquid to a gas, or boiling, we have essentially completely destroyed, completely broken all of our intermolecular forces, that we have separated every molecule from every other molecule, and there's very, very little interaction. There is a little bit when two gas molecules happen to get close to one another, but most of the time those particles are pretty darn far apart, so the intermolecular forces are very minimal. So we can see that in both of these phase changes, melting in boiling, we're changing something about our intermolecular forces. So in the case of melting, we're just disrupting some of them. There are still quite a few interactions between our molecules in a liquid, but when we get to a gas, they're effectively all gone. So what this means is that the melting point and the boiling point are going to be affected by our intermolecular forces. So the melting point is just the temperature at which something melts, and boiling point is the temperature at which something boils. So because melting kind of only disrupts some of our intermolecular forces, it's less of a direct relationship. But in general, substances with stronger intermolecular forces usually have higher melting points. The stronger your intermolecular forces are, the more energy you have to put in to disrupt them, that you have to put in more energy to pull your molecules apart. The stronger your intermolecular forces are, the harder that is to do. So that means it's going to require a higher temperature. But because we're only disrupting some, and exactly how much is going to vary by substance, this is usually true, but not always. However, with boiling, because we're essentially completely breaking all of our IMFs, boiling is actually a very direct relationship between strength of the intermolecular forces and boiling points. So substances with stronger intermolecular forces usually have higher melting points and always have higher boiling points. So boiling points are a very clear way to tell whether something has stronger or weaker intermolecular forces. So a couple of examples to wrap things up today. First up, which would you expect to have a higher boiling point and why, H2O or H2S? So for this one, if we look at our two structures, we will have very similar molecules, the only difference being the central atom of oxygen versus sulfur. So the key difference in these things, they're both polar molecules, they both have a bent geometry as I've drawn them. But this one can hydrogen bond because it contains oxygen-hydrogen bonds. And this one cannot. So because of that, this one almost certainly has stronger intermolecular forces. So that is the one that we should expect to have the higher boiling point, because anything that has stronger IMFs is always going to have the higher boiling point. Those two things go hand in hand. So we can also go the other way. If we have data provided to us based on the data below, which has the strongest intermolecular forces, looking for the highest boiling point is all you need to do. So the highest boiling point we were given is here, means that CCl4 has the strongest intermolecular forces. So you don't have to think any further than that. But I do want to point out that this is kind of an interesting case, that CH4 is nonpolar because carbon-hydrogen bonds are nonpolar. CCl4 is nonpolar because it will have a tetrahedral geometry that is completely symmetric. But CH3Cl is polar. So normally, based on what we had talked about in the previous video, we would expect the polar thing, since it has dipole-dipole interactions, to probably have the strongest intermolecular forces. But since we have other data available to us, we can see that that's not the case. That in CCl4, this one is enough larger that the London dispersion forces are actually stronger than the dipole-dipole forces in this polar compound. So if I were giving you this list without, so if I gave you this list without the boiling points and asked you to predict, I would probably expect you to pick the polar one as having the stronger intermolecular forces, and that's totally normal based on what we've talked about. There's no good way to predict this otherwise. But since we're given the boiling point data, we can conclusively say that this one must have the strongest intermolecular forces because it has the highest boiling point.